So again, good morning and welcome to the Robotics and Automation TC webinar number 33, November 2015, where we have Joe Davidson and Abhisesh Silwal from Washington State presenting their work on robotic apple harvesting in Washington State. Robotic apple harvesting is a very challenging technical endeavor, but it's not only a very challenging technical work, it is also a very important economic work. In the U.S. and in many countries, there are always preoccupations, concerns with the availability of labor for harvesting fresh fruit, and that will be in part solved by our people like us developing robotic or automated harvesting systems. And what do you know, Joe? We are up to 21 people. We are going up by the minute here. So again, it's a great pleasure to have Joe and Abhisesh present their work, including the challenges and the results they have obtained in the recent past in developing systems for automated harvesting of apples in Washington State. For those of you who don't know, Washington State produces about 60% of all apples in the U.S., and therefore this is a very important, again, economic and technical work. Joe, he comes from a military background. He got his degree at West Point in 2004. And after a stint at the Mechanical Engineering Department at Washington State, where he got his master's, he is now at the School of Mechanical and Materials Engineering, also at Washington State, for his Ph.D. Abhisesh, he comes from Nepal, where he got his master's in mechatronics, where he got his bachelor's in engineering in 2009. Then he went to Thailand to get his master's at the Asian Institute of Technology in 2012, and now works with Joe at Washington State also as a PhD student. So Joe and Abhisesh, let me pass on the microphone to you guys. Just one last thing. Everybody please click on the person icon on Join Me and change where it says viewer to your name. And finally, remember to mute your phone or your microphone. So now let's get the miracle of technology to work and pass the presentation to Joe. And we're good. So I'm going to mute my phone. Everybody use the chat window to ask questions or just unmute and ask questions directly on the phone. Joe, thank you, and Abhisesh, thank you again.
Okay. Thank you, Marcel.
Thank you very much.
Good morning. My name is Joe Davidson. I'm a PhD student in the School of Mechanical and Materials Engineering at Washington State University. I'm joined by my colleague, Abhisesh Silwal, who's working at the Center for Precision and Automated Agricultural Systems, which is also at WSU. And WSU is a land-grant university in the far Pacific Northwest of the United States. So before we get into the bulk of the presentation, we'd just like to acknowledge and thank the United States Department of Agriculture, who's funding this research through the National Robotics Initiative. This is a collaborative project with horticulturalists, agricultural engineers, and mechanical engineers, and we're just beyond the halfway point of the project. So I'll start off with just some background motivation for why we're conducting this research, talk about the specific working environment of our system, then present the objectives that have guided our design. Also talk about some preliminary results we have from hand-picking dynamic studies of the apple picking process. We'll then present the machine vision design and the mechanical manipulation system design. We'll have some field testing results, preliminary results we just have from the most recent harvesting season over the last couple months, and we'll show a short 3-minute video that shows both the good and the bad of how the system's operating right now. And at the end, we'll just present some of our future work for the next couple years of the project. So as Marcel mentioned, in Washington State, the fresh market apple industry is a big business. And when I say fresh market apples, I'm talking about apples that you would find on the shelves of your grocery store, and that's opposed to, in contrast to processed market fruit like juice apples. Those fruit have a higher tolerance for bruising and external defects. But last year, the state produced just under 3 million metric tons of apples. It's valued at just under $2 billion US dollars. And it's far and away the largest producer of apples in the country. It's also a major international exporter of apples. In production, the most time-sensitive and labor-intensive task is harvesting. There's always a critical risk of not having the right people at the right time. And in Washington State alone, the harvest requires the employment of a semi-skilled seasonal workforce of up to 30,000 additional workers. And it's also expensive. Local growers say that it constitutes approximately a third of their annual variable costs. Those costs are rising, and as Marcel mentioned, like what's happening in many agricultural sectors around the world, there's always increasing uncertainty about the availability of the labor pool. And there is no mechanical harvesting for fresh market apples. So other than a few exceptions, apples are harvested like they were just almost 100 years ago with ladders, buckets, and a lot of labor with highly repetitive picking motion. So the lack of mechanical harvesting is a problem that's receiving a lot of attention from the United States Department of Agriculture and the state and local organizations. So the long-term goal of this project is to reduce the dependence on the seasonal labor force for fresh market tree fruit harvesting. And this objective, the objective of the project is to create a framework for knowledge transfer and collaboration between human and machine for effective harvesting. And we came to this objective based on some earlier studies that showed that both knowledge of fruit growth habits and the hand-picking process are fundamental to developing effective harvesting techniques. And as most of you probably know, there have been quite a few efforts to develop robotic harvesters in the past, but challenges such as speed, cost, and robustness are still limiting commercial adoption. So we aim at advancing the technology one step further in some or all of these aspects.
So this slide talks about apple cultivar practices. A traditional apple tree is a three-dimensional structure with branches protruding in every possible direction. And implementation of robotic system to harvest apple in this kind of unstructured environment is very difficult and challenging, which is why modern cultivation practices with proper thinning, pruning, and training have simplified this scenario to a two-dimensional planar canopies with branches protruding towards only in the longitudinal direction and fruiting along the trellis wire system. The images shown here are from such a system. It's an image taken in a commercial orchard here in Washington. The system is particularly a tall spindle architecture. The image on the left-hand side is a V-trellis wire system, whereas the image on the right-hand side is a vertical trellis wire system. So we've implemented our robotic harvesting system in this kind of modern or formal tree architectures. Moving on to slide number 7. So our design objective here is to implement a harvesting system that has a harvesting cycle less than 6 seconds. What's underneath the harvesting cycle we'll discuss in more detail in our upcoming slides. We intend to have detachment success more than 90% and fruit damage according to USDA standards of less than 10%. We will be applying our robotic harvesting in multiple varieties of apple. And our design is a modular design, which is both manufacturing and cost-effective. So our overall approach is an under-sense design, both from mechanical and machine vision perspective. We only need to execute the machine vision system once at the beginning of each harvesting cycle. So it's a look-in, move-forward fruit picking technique. Our mechanical design is robust, has a good robustness to position error, as well as it's entirely based on replication of human hand-picking process.
So, as we mentioned before, that we did some studies on the manual apple picking process with professional apple pickers just to help guide the design and development of the End-Effector. And based on watching them, it's clear that what they're using to pick the fruit is a spherical power grass, according to the grasping taxonomy. So it's a grass designed for security and stability rather than dexterity. Depending on the apple variety being picked and the length of stem, they will typically apply their index finger against the stem, and that's to try and help shear the joint with the tree. The shear strength of that stem abscission joint is quite a bit less than the tensile strength. So like I said, there's no dexterous manipulation of the fruit with the fingers other than placing the index finger against the stem, and again, that's cultivar dependent. And then they'll apply a pendulum motion where they simply twist the fruit off the tree. So though our goal was to replicate the human picking process, we quickly discovered that trying to replicate that exactly with a robotic system was going to be problematic, and primarily because the human picker has very good sensory knowledge of the fruit's orientation and the direction of its stem, and the human picker is also very aware of the immediate surroundings. They know the optimal way to twist and remove the fruit based on adjacent fruit, obstacles like trellis wires and main branches. We found that trying to identify the stem and orientation of the apple while it's on the tree is quite challenging, specifically because for some fruit you may not even see the stem above the stem cavity of the apple. So what we did was look at trying to determine if there are effective techniques to remove the fruit that are irrespective of its orientation and stem location. So in this sense we call it undersensed hand picking. And you can see a couple of different pictures of the experimental setup we had. On the left, you can see we have flexible force sensors on the thumb, index finger, and middle finger with a gyro and accelerometer on the back of the hand that measured rotation of the fruit around the axis of the forearm. And then we applied different picking patterns, 4 different picking patterns, trying to replicate a robotic approach to the fruit where it follows an azimuth angle and then does a rotation around that azimuth angle, and see if there is an optimal way to remove the fruit that results in lower normal contact forces as well as lower rates of stem pulls on the fruit. So what you see here is just a plot. This is a plot of one sample, a representative sample. On the top you have, when I say one sample, that's one fruit. On top you have the normal contact forces on the thumb, index finger, and middle finger. On the bottom you have the gyro output of rotation around the axis of the forearm. It became pretty clear to us exactly what was happening during that dynamic sequence of picking the fruit, where initially the fruit is lightly caged, grasping forces are low, and then approximately at 0.8 seconds, those normal contact forces increase rapidly as the hand begins to feel the external disturbance of the stem strength to the tree while it tries to pull the fruit away from the tree. And then those contact forces peaked just after a second, and that dashed line essentially shows the point where the stem's attachment to the tree was severed. So at that point, the normal contact forces decreased as that external disturbance of the stem was removed. So it gave us an idea of exactly what kind of normal grasping forces could be expected during the picking sequence, as well as the average angle of rotation if you were to apply a pull and twist motion. So this slide shows the mechanical design of the system that we're using. It's a custom design, essentially 7 degrees of freedom. There's a 6 degree of freedom arm mounted on top of a mobile base. And I say currently using because it's a modular configuration that uses the Dynamixel Pro actuators. So they're relatively easy to interchange and change the kinematic framework of the design. So for the first round of field testing that we just did, we were essentially looking for a minimum of 6 degrees of freedom to have arbitrary position and orientation of the end effector within the workspace of the manipulator. In the future, we have a parallel effort ongoing right now to try and actually optimize the kinematic design to match the environment. So that's still an opportunity for improvement for system performance. And that mobile base you see, that was just something we made with a stepper motor and some timing belts and linear bearings. So this is the end effector that we use for the first round of field testing. It's an under-actuated device, so like is seen within the robotics grasping community at large, under-actuation has become very popular. It provides a shape-adaptive grasp, so it was advantageous that it could be applied to fruit with different shapes. There is quite a bit of discrepancy between the shapes of individual apples. And then it incorporates passively compliant joints, and that passive compliance has been shown in a lot of research to enhance both robustness to position error and the robustness to unplanned collisions. So those joints can twist out of plane and still not fail. So We viewed both that robustness to position error and robustness to unplanned collisions as very advantageous for this specific application. And then right now, grasping is executed in an open loop manner, so there's just a stall point on the actuator torques, and those actuators are driven to their stall point, assuming the grasp is complete, and then the arm essentially removes the fruit at that point. And everything you see on there, except for the actuators and fasteners, were fabricated with additive manufacturing, so just simply using a 3D printer, desktop 3D printer. And so overall cost for the end effector was relatively low, as was the total weight of the device.
So our vision system consists of two cameras in a vertical rig setup. The camera on top over here is a color CCD camera, whereas the camera on the bottom is a time-of-flight based 2D camera from BMD Technology. So we acquired the color images of the canopy using color CCD camera. The vision system uses color, shape, and size information to identify apples, clearly visible apples, partially occluded apples, as well as individual apples within clusters. Two instances of the output of the vision system can be seen in block number 2. And we fused this identified apple with the point cloud obtained from the time-of-flight 3D camera to localize this apple. One such instance of fusion is seen in block number 3, where the point cloud is just pasted on top of the color image. So moving on to another slide, this shows our overall robotic harvest system setup. Everything is, including the robotic arm, cameras, and the computers, are mounted on top of a gator. The robotic arm and the cameras are on top of a sliding aluminum mount. The camera is the robotic arm is approximately about half a meter away from the camera, and currently we're placing the camera about 1.5 meters away from the canopy. We can also see that the robotic arm is directly in front of the camera. And we did this experiment in a commercial orchard here in Washington under broad daylight conditions. So this slide shows the overall hardware architecture of our system. We're using a 5,000 watt generator to power our system. The six dynamical motors runs under 24 volts, whereas the end effector is in 12 volt system. The PMD cameras are connected via USB interface, and the camera is a Giga 8-bit camera. The sliding mount is controlled with a stepper motor, and all of these communication protocols are with a serial comm. So we'll show you a video, a 3-minute long video of our system, which has both failures and challenges in our harvester. So currently we're just picking and dropping the apples as with the robotic arm. So now we're showing the limitation of our robotic harvesting so far. And we'll discuss about all of these limitations in detail in the upcoming slides. So I hope the video ran smoothly over the internet. So moving on to the next slide, one of the major challenges of applying machine vision system in outdoor environments, such as an orchard, is variable lighting condition. Two instances of such a variable lighting is shown in this slide. On the left-hand side, the image on the top shows overexposed image, whereas the image on the bottom shows underexposed with shadows. In both instances, information of color as well as shape is lost, which is quite essential for the machine vision system to identify apples. So rather than having a very time-expensive post-processing, we focus more towards acquiring better images. So we implemented a technique commonly known as exposure fusion, where we acquired several images with different exposure values and then merged them in a very in a certain way that the resulting image turned out to be quite good in terms of exposure as well as intensity distribution. Two instances of recovered image are shown in the right-hand side of the same instance that was quite badly acquired. So moving on to slide number 18, in order to better understand the performance of our system, we segregated and timed all of the major or essential components of our system. For instance, the machine vision system, the timing starts from image acquisition to apple identification, and then moving towards 3D coordinate mapping, as well as filtering out all of the apples that are too deeper into the canopy. Inverse kinematics time starts by calculating the joint angles and velocities, calculating the distance that the base is supposed to move, as well as discarding fruits that are beyond the reachable workspace of the manipulator. And the picking time is the time to solve the traveling salesman problem. We over here we're using traveling salesman problem as a optimal way to prioritize apple for harvesting, as well as the picking time also includes the approach to pick the apple along the azimuth angle, grasping, picking, and dropping of the fruit. So the overall harvesting cycle consists of the vision time, inverse kinematics time, and the picking time. So I'll talk about the vision accuracy here. So we implemented this robotic harvesting system in 54 harvesting cycles. So as I mentioned earlier, that we need to take image only once at the beginning of each harvesting cycle. So total number of image equals to total number of harvesting cycle. The manual count of apple in these 54 cycles were about 193. The vision system worked perfectly. It identified all of the apples correctly. There were around 150 apples in the reachable workspace of the manipulator. Average number of fruits per image was about 4 apples per image. On average, the vision system that includes image acquisition, identification, 3D point cloud mapping, and depth filtering took around 6.3 seconds, which brings the vision time per apple to about 1.7 seconds.
So as Abhisesh mentioned, there were approximately 150 fruits, or not approximately, there were 150 fruits that the system attempted to pick. It successfully detached 127 or 85% of those fruit. So not quite as high as our initial design objective stated, which was 90%. The majority, every fruit that was picked, we inspected to see whether or not it had its stem attached, whether the actual spur detached along with the fruit, or if it was rather in just a perfect condition with the stem and no spur. The majority of the fruit had the stems attached. However, there was a significant percentage that the spur detached along with the fruit. So that's problematic in the fact that detaching the spur, one, potentially removes a fruiting position for next year's crop, as well as that's just an extra step that would have to be an extra step to remove that spur before it would go in the storage container, the final storage container, to ensure that spur wouldn't damage adjacent fruit in the storage bin. So the misses, those 23 fruit that weren't detached, can generally fall into 5 general categories. You saw some of them in the video. The first category was what we called essentially a poorly thinned branch, where an apple would rest on a long, thin, flexible branch that wasn't attached or secured in the vicinity of the trellis wire. So it would essentially act like a pendulum, where when the grasping is executed in an open loop manner and when the end effector pulls the fruit back, the fruit just swings like a pendulum out to the release point and never actually gets detached from the tree. The second error, which we had 3 occasions of, was the finger on the end effector grabbing an adjacent obstruction, and that was primarily main branches and sprinkler lines, so it couldn't complete a successful grasp. There was also 8 instances of position and or calibration error. Something that we found that was kind of interesting was that the calibration between the mechanical system's reference frame and the camera's reference frame would change as the temperature profile of the 3D camera changed. So not quite sure why that's occurring, but that's something we're going to continue to study. Also, we had 2 instances where the fruit slipped from the grasp. Essentially, those were fruit that weren't quite as mature as the neighboring fruit. They still had some green on the backside, and so the stem strength of the tree was very strong, and the end effector wasn't able to detach those fruit. Finally, what you saw in the video was that a previous fruit stuck in the hand on 3 occasions. So if a spur detached, or if it was one of those fruit that was like a pendulum fruit, it would stick in the hand, and so it couldn't go to the next fruit in the cycle and pick it. We didn't see any obvious evidence of bruising, and it was clear to us that based on this preliminary testing, that the ideal fruit location was approximately 3 to 6 inches away from the trellis wire on thick main branches. So overall picking time, again, this is a measure of just mechanical manipulation. It doesn't include the upfront vision processing. So mean picking time was 6 seconds of fruit. So if you include the vision processing, overall cycle time was 7.7 seconds. So a little bit higher than we were shooting for, so we need to have some additional work there. But when you look at a cycle of the fruit in a cycle, the first fruit in the cycle always took the longest to pick, and that was because it was essentially the furthest away from the ready position of the manipulator. Every other fruit in the cycle, the average time for those fruit was 5.8 seconds. And on the bottom bullet here, we segregated every subtask in the picking process as its own discrete function in the software and timed it. So we could see which subtask was requiring the most execution time and which one requires additional focus in the future for reducing that overall picking time. So you can see far and away approach to the fruit was taking the most time. So approach to the fruit includes that going to that first fruit, and then the sequence for the following fruit in a cycle. The approach is the travel distance from the first fruit to the next fruit, and so on. So that's an opportunity for improvement. If we can reduce that time, we could make some improvements in the overall picking time.
So based on our field experience, although the tree canopy were very planar and 2D in structure and greatly simplified for robotic harvesting, there were several instances in which the robotic end effector would come in contact with the trellis wire or branches or trunks or adjacent fruit itself, and could potentially damage the end effector as well as damage the adjacent fruit. So we not only need to identify apples, but we also need to identify trunks, branches, and trellis wire as obstacles and try to avoid them as far as possible. We also need to identify apples that are very close to the trellis wire, as well as clusters as whole, and have a higher level decision based on the obstacle detection for a very intelligent way of picking these fruits under very close to the obstacles. As Joe mentioned earlier, that the grasping mechanism, that the current grasping mechanism is an open loop system. So if we miss the fruit, then it continues to grab the fruit, which is something that's time consuming and something that can be avoided. So we're planning to add a tactile sensor on top of the fingertips so that we know for sure that that we are grabbing the fruit and avoid these kinds of unnecessary scenarios. So these are some of the future work that we'll be implementing in our upcoming research. And that is all we have for today's presentation. Thank you very much for your attention, and we'll be glad to attend and answer your questions and comments.
Gentlemen, thank you very much. Very interesting results, much more advanced than I've seen in the past. And not only you're showing that this is potentially a solvable problem, you're showing that there's lots of room for improvement there with respect to the timing and everything. So thank you again, and let me open the mic here for questions. The microphone or the chat window are open for everyone to ask questions.
I have a question. This is Paul Heineman calling from Penn State. You had, well, after the picking process, are you thinking about, so how would the arm then deliver the apple to the bin or whatever kind of mechanism or collection point that you would use?
Sure. That's a great question. So obviously in the video, the hand was just dropped. In this round of testing, the fruit was being dropped in the field. I think right now for this next round of field testing, we're going to obviously scale the system to be able to reach additional portions of the tree. It's limited right now to operating between 2 trellis wires. So we're going to expand the scale so it can cover more of the tree. And then I think right now we're considering a vacuum assist system, something that can be used to minimize the amount of travel time from the picking point to the actual storage location. So I think right now our conceptual idea is a vacuum assist system of some kind.
Okay, thank you.
We have a question on the chat window. Did you consider other types of end-effectors that were not modeled on hands/fingers?
Where was that question, Dr. Burton?
It's on the chat window. Did you consider other types of end-effectors that are not modeled on hands or fingers?
Yeah, we are now. Initially, we were really interested to see if we could replicate the human grasping process. But the human grasping process is so selective to the location of the stem that it's problematic and difficult to replicate the grasping process like the human picks the fruit. And so, we are considering right now implementing something that might use pneumatics or vacuum to assist with the picking process. We don't necessarily think that fingers and a grasping design is the be-all solution to picking the fruit, that there may be a better way to do it, and I think we're looking at considering vacuum. We had discussed preliminarily a cutting device that uses some kind of blade, laser, whatever, thermal method, mechanical method of cutting the stem. And, previous work that they actually, I remember 1 or 2 papers where they actually cut the stem of the fruit. It was always with the Fuji cultivar. And when you look at the stem length data, the Fuji has the longest stem, at least of the apples that of the 5 we tested, the Fuji has the longest stem. And so it seemed to us that it may be possible to do that on a Fuji apple, but with some other fruit where the stem doesn't even extend beyond the top of the apple, didn't really see a good way to access the stem without damaging the fruit if you were to use a cutting mechanism.
Yeah, the folks at WUR in the Netherlands, they have been experimenting with those kinds of devices, sucking and cutting, and even a little blowtorch that cuts this, not cuts, but kind of burns the stem. But they are using those mostly in indoor environments. Any other questions? Joe and Abhisesh, just so you know, we reached a peak of 33 people during the webinar, which is very high. Didn't beat our record of 40 in October, but got very close.
Okay.
It was very great. I was wondering about your thoughts on looking at the harvesting problem from a higher level systemic perspective. The other day I was talking to a journalist here in the U.S. who was asking, why is it easy to do autonomous spraying and it's hard to do autonomous harvesting? And we were discussing how they are different. And one of the things I was explaining to this person is that it could be that we, in fact, never end up replicating, so to speak, the human being in the harvesting operation, but instead we change the horticulture of growing apples so much that changing the format of the farm plus adding automation solves the problem together. You see, as opposed to let's try to use the farm as it is today and develop a system for autonomous harvesting. So
right.
You guys are some of the strongest people anywhere in the world working on automated harvesting. Are there any thoughts? Is there anyone looking at the problem from that perspective of completely redoing the farm so that it's even more automatable?
Very well. We've had preliminary discussions. There's an orchard about 2 hours north of where we are. That it's a very famous orchard with an international reputation, and they actually spend, when you talk to their managers, they spend more on thinning and pruning of the orchard. They hand thin and hand do blossom thinning by hand, which most orchards do that chemically. So the distribution of the fruit, it's pretty incredible when you go to the orchard. They're very well distributed. There is no vegetation other than a few leaves on top of the apples to protect them from sunburn, and clustering is minimal. So what we're trying to do is work with those orchards, that specific orchard, to identify within reason, within what's reasonably horticulturally, how can they get the fruit distributed optimally to match what we think would make it most realistic to do a mechanical methods of harvesting with robotics. So looking at distribution of fruit away from the main trunks and trellis wires, what kind of supporting branches those fruit are on, and how they prune and thin their vegetation to make it so it's easier for the visual system to detect the fruit and there's fewer obstacles during manipulation. So that's something we're trying to work on in parallel and identify right now.
Yeah, that's great. I know that these folks have been changing completely the physical infrastructure of the orchard in the last 15 to 20 years, and to change that again would be a lot of work and a lot of research. Another question on the chat window here. Are there open challenges in the vision system? What drives the long processing time in the vision pipeline?
Yes, there are. Whenever we go to outdoor environments, there are a lot of challenges in terms of vision. Basically, three in terms of robotic apple harvesting. The first one being as I mentioned earlier, a variable lighting condition. Depending on what time of the day, the lighting condition, it changes rapidly. The other challenges are from clustering and occlusion. Clustering meaning that apples are very closely packed with each other, and occlusion means that the view of the apple is blocked by another apple. Again, this and the vision system that we developed, it basically uses circular Hug transformation and blob analysis for to identify apples that are clearly visible, as well as individual apples in clusters. And the process of doing this circular Hug transformation and blob analysis, it's quite computationally expensive, which is why a single image takes about 6 seconds. On top of it, we're taking multiple shots of the canopy, and then with the different exposure values, and then merging them together to control the variable lighting condition. That also adds timing, which is why the vision system is quite computationally expensive, and I think that's it from the vision side.
Very good. Another question here in the chat window. What is the state of the art of fruit robotic harvesting, and how do you benchmark your work compared to other previous and current studies?
So that's a good question. So, robotic systems have been tried for numerous applications with numerous crops, and so that includes fields, greenhouses, orchards, with all different kinds of crops, especially specialty crops. And I know there are some commercial prototypes that are out there. I'm not aware of any widespread commercial implementation of harvesting systems for specialty crops, and that's primarily because of problems with speed and overall detachment rates. If trying to compare what we're reporting so far with other ongoing work, I think maybe something that maybe is unique about what we're talking about here is just using a global camera and having built-in mechanical manipulation or built-in mechanical robustness to position error. A lot of systems so far have had problems if the end effector had a couple millimeters of error of actually successfully detaching the fruit. We've so far been able to see that even with a couple centimeters of error, the end effector can still complete a successful grasp. When you look at overall harvest detachment rates, and I'm going to compare specifically to robotic apple harvesters. It's hard to compare this system against systems for all different kinds of specialty crops. For robotic apple harvesters, cycle times have been in the neighborhood of anywhere from 8 to 15 seconds. So this cycle time would represent an improvement upon those. Again, it's somewhat difficult to tell when you look at the literature what's included in a cycle time. The reporting criteria aren't necessarily consistent, so it's difficult sometimes when you look at the field to determine whether or not cycle time includes every subtask required for the picking process or only a certain few subtasks. So, and the overall detachment rates for robotic apple harvesters, I believe, have been in the neighborhood of 75%. And you see here that I guess for apple harvesters at least, one of the big problems has been stem attachment. And I know there is some additional research going on right now about determining whether or not having the stem is truly important for market acceptance. There's been some preliminary studies that show that having the stem pulled out may increase the susceptibility of the fruit to disease post-harvest. I'm not sure that's exactly conclusive, so there's some work going on to see whether or not if the stem pulls out but the fruit's not damaged during that process, is it still okay to go to market? And if they can determine that would significantly remove a constraint of robotic apple harvesting. So because what you can see, even though we have approximately 85% detachment rate, there are a significant percentage of the fruit that come off either with their spurs or the stems detached. Bruising hasn't really been a problem.
It's certainly a work in progress, and it's an advance over other works I've seen before. Any other questions? Okay, Joe and Abhisesh, again, thank you for this holiday gift. It was a great presentation, great work. I invite everybody to be attentive to their email. We are going to have our first webinar of the year next year, sometime on the week of January 18th, with the Agricultural Robotics and Automation TC Lightning Round. Again, you're going to have 1 minute to present one slide about your work, your lab, your research. I'm going to start collecting those slides sometime in early January and schedule that at sometime soon again. So thanks everybody, happy holidays, and I'll see you in 2016.
Thank you, bye-bye.
Thank you very much.